All right, good morning, everyone. Thank you for joining for our panel. My name is Brian Wendamu.
And I'm Emily Clark. We are co-leads for the Cold Plate Subproject. And yeah, we're excited to put this panel together. Burhanu, can you tell everybody what we're talking about today?
Yeah. A couple of years ago, we were talking about, tens of, kilowatts power rack, and then, it's not long ago again. It's hundreds of kilowatt. A megawatt is a conversation now. And during the keynote, we heard even the gigawatt data centers. So it's a big topic to cover, and then we have industry experts, from you guys, and we'd like to introduce them.
Yeah. So we have Paul Artman in the middle. Say hi, Paul. Paul is a fellow in system design engineering in the data center system group at AMD. Paul focuses on emerging technologies to enable and scale the industry on direct liquid cooling. And Paul has more than 20 years of experience in thermal, power, and hardware engineering, hardware packaging. He's a founding member of ASHRAE TC 9.9. On the end, we have Husam Alissa. He leads the system technology team in Microsoft's CTO office. Husam drives the development of next generation technologies across the stack from the chip to the data center, advancing the future of cloud and AI infrastructure. Husam has over 70 technical publications, 1 authored book, and over 100 filed and granted patents. So thanks for joining us, Husam. Chris Campbell, hey Chris, is a global product manager for liquid cooling, fluid distribution at Vertiv. He has over 16 years of experience in mission-critical cooling systems. Chris has been a member of ASHRAE for 11 years and currently serves as the secretary for ASHRAE TC 9.9. So please welcome our panelists. So Burhanu told us why we're here today, so let's set the stage for our audience. So Paul, maybe could you tell us what's driving the need for these high power racks?
Yeah, I just want to thank everybody for coming. It's just amazing that we're, 5 years ago, thermals was an afterthought, and now that it's in every keynote, we're talking about thermals and power and how we get higher. And why is it becoming critical? It's just the interconnect. We're seeing tremendous value from scale-up AI, and how you get there is interconnecting, trying to stay in copper. And so that drives density. With that density, you're requiring new cooling technologies. I think for the most part, the hyperscalers and everybody would love to stay in air cooling. It's a run rate business that works really well. It's easy to do. But we're going to transition to liquid just because of the density. So we see a huge ramp on the amount of liquid cooled systems going from what I would say kind of a cottage interest in HPC to just huge volumes, talking about 5,000 CDU a month kind of volumes in the industry. So it's just where we're headed. There's other technologies that could be interesting. We're looking at immersion, something that could be interesting for the edge. But when you look at these kind of powers and really the interconnect, it doesn't lend itself to immersion. And then as you look further, we're looking at, I think two-phase could be interesting, is something that we're all looking at. But then it's very disruptive. And then what we really want to understand is chip to data environment. So clearly you can get a better cold plate, but where do we drive two-phase? So it's really interesting times. We're scaling out DLC. We're talking about 1,000-watt chips all over the place, megawatt rack. So it's very challenging. I would say the other thing kind of interesting is rack. I don't think these are racks anymore. If you see the ultra-wide, the overview ultra-wide or wide, and some of these things, they're more like pods, but just really challenging times.
Yeah. Husam, do you have anything to add to that about what's driving these high-power racks today and what technologies we're looking at?
Yeah, thanks, Emily. I think if we go all the way to the chip, we're looking at more features, more clock speed, more cores. All these things are driving SoCs to have higher power. And also, if you look at GPUs, so we have the SoC, but we also have the HBM. And the HBM itself, 3D stacked, low. Maybe the power is not as high, but it requires colder temperatures to actually deliver the performance that you want. So those are some of the challenges coming at the chip, requiring better cooling, better elimination of the thermal resistance layers. So that's at the chip. And then we take it to the rack. If you have a lot of these chips in a rack, And again, I know we'll talk about different technologies, but we're talking about liquid cooling here, say 1P DLC. How are you going to get all that liquid in to cool those chips, route it the right way? We're trying to define the LPM per kilowatt and how that range changes. Inlet temperature is a big deal. Like, what is the temperature that gives us the best performance at the chip? But at the same time, we have to optimize across the stack. We need to think about the data center, because those temperatures have an implication to the data center PUE. So it's exciting time, and it's also an opportunity to do this cross-stack optimization, where we look at the performance of the chip, how it impacts the rack architecture, and then how it impacts the data center. And it's really not just a cooling thing. You actually have power, cooling, and network. They're all influencing each other. So you could have a breakthrough in network that changes the density roadmap. So all these things influence and affect each other. And again, it's a nice opportunity to do cross-stack optimization.
Thank you.
Yeah, awesome. So the application guys say, hey, your chips are getting hot. And then the guys working on this side, hey, the application you're running are getting the chips hot, right? So, and these AI workloads, everybody's taking advantage of. So it's nobody's fault, it's everybody's using it. So how do we figure out how to do work around? So it comes to the cooling. So what are the cooling options to address these high power racks? Maybe Chris?
Yeah, sure. So we've heard in some of the other talks in the last couple of days about how the speed of deployment of these data centers is pushing everyone to find real estate and find power where they can find it. So there's a lot of lack of standardization in many areas right now, hence the work that OCP does. And part of that also includes the different types of CDUs and heat rejection technologies that are being used. So we see things like liquid to air and liquid to refrigerant, which are being used a lot for transition technologies, for retrofit opportunities. Maybe if you have data centers that don't have water available, if you have a direct air economized data center, for example, you might use some, use some like liquid to air where you can actually reject into the space and take advantage of the heat rejection that you already had. Or for some liquid to refrigerant systems, if you had like DX perimeter cracks and you wanted to replace those with something that could do liquid cooling single phase direct to chip, you could replace those and keep some of your heat rejection technology. So those things are happening sort of to get us by and to reuse some of the existing infrastructure that's already out there. Beyond that, we also see obviously the stuff that you'll find out on the trade show floor here and at other trade shows like the in-rack CDUs and row-based CDUs. And then moving on towards like the Deschutes stuff that you see out there with skidded CDUs more for gallery and perimeter. So there's a couple of different reasons to choose those technologies. We see a lot of deployment of both actually in-rack and row-based CDUs. So some of the rack-based CDUs will allow you to deploy rack scale. So all of your TCS piping and your PG loop is all inside the rack. So you can then bring the racks in and deploy rack by rack at rack scale. When you go to, of course, you have to then bring primary fluid to all those racks, but you're not dealing with like the larger diameter stainless steel piping that you would have overhead or underfloor for row-based CDUs. So there are some trade-offs there for in-rack CDUs. You also sacrifice some rack space, obviously, but it's a more like Lego block, building block approach to being able to do rack scale solutions. Then you can do more of a pod-based deployment where you'll have your row-based CDUs feeding multiple racks. You can obviously take advantage of economies of scale there. You don't have individual pumps in every rack and things like that, but you're trading that off by needing to have those larger diameter stainless or other approved material piping going from your CDUs down your row, serving all the racks. You have more fluid distribution you have to deal with as far as flow rate per the rack and things like that. So there's definite trade-offs there for those two. And then as we see Deschutes and other skidded-based CDUs, there's opportunities there where you can take advantage of even more economy of scale. But again, you're trading off potentially larger pipes, more fluid, a larger blast radius if you have certain types of failures like leaks or fluid quality issues or things like that. So there's a lot of trade-offs, a lot of different solutions going on right now, and there's always these problems to solve of trying to figure out where it makes sense to standardize.
Thanks, Chris. Anybody else have anything to add about CDUs and
again, it's one of those really interesting times. I think in-rack CDU really makes sense for some deployments. Service gets hard. Failures are maybe not the redundancy. I do think that 1.5 to 2.5 megawatt kind of row is really interesting now for colos and others people where it's just a run rate business. What's really interesting is you get bigger and talk 7 to make 5, and you're talking about 10 megawatts, and you start talking blast radius and service. That's the more interesting, I think, and how you adopt it. I think we have to have like kind of standard run rate CDUs, which you see people like Vertiv make and Schneider, but then you see these kind of custom ones. It gets really interesting, and to me, it's not obvious on, is it getting too big and it's a huge blast domain? How do you service it at the amount of fluid that you're talking about? How do you manage its transients? But it's really interesting, and it does make sense that, move the, you want to move the CDU as much as possible for AI out of the way. You want to put all, I talked about all copper as close as possible. So the pruner makes perfect sense, but is it going to get too big? How do you scale it? What you tend to see is a CDU for architecture. So you're not going to see a Dell mixed with an HP or an NVIDIA mixed with a Microsoft. So how do you manage that? You see huge variance in CDUs when we talk about flow rates, filtration, pressure. So yeah, it's really interesting. I do see that we're going to see some emerging swim lanes, but that perimeter is going to be really interesting to watch.
Awesome, thanks.
Yeah, I want to just take one step back. Like if we look at all of our options or the cooling options, 1P and 2P cold plates, 1P or 2P immersion blades or immersion in tanks, even all the way cryogenics is mentioned sometime. But really, the shortest time to market and what the industry is scaling right now is 1P, PG25, maybe other iterations of the coolant, direct to chip. And focusing on that and the enablement of that, I think that through the journey, I remember it from 2020 and 2019 when we were initially saying, well, there are a lot of large air-cooled data centers at hyperscale, and we bring these liquid cooling equipment to them. I just want to enable a liquid-to-air interface. And back then, the discussion was it a rear door that is used as a radiator or a sidecar? And there was a lot of work that we've done on analyzing the pros and cons. And I think there's more convergence on sidecar, and that's where we have more products like Microsoft Callan and other liquid-to-air enablement for liquid cooling. But then the natural next step is liquid-to-liquid CDUs, and this is what also being deployed at scale. But then here we get to another it's thought-provoking. Well, how big is a CDU? Well, here are a couple of thoughts. One, you need the kilowattage out of the CDU. Number two, it needs to have the pressure head. And you need both of these to match. Actually, you could, looking into a spec of a CDU, you could have higher rating and capacity, but it needs to be matched with flow rate. This is very important, especially as we're going to higher flow rate requirements. Now, the CDU capacity itself, 1 megawatt, 2 megawatt, more or less kit CDUs, and as Chris also highlighted, you're doing this trade-off between blast radius, cost. We're also looking at the rack density roadmap, and the title of the session, if we're going to go to 1 megawatt racks, we're going to have like one CDU, one rack. Does that really make sense? So that's one way to think about it. There's like even going all the way and saying, all right, I'm probably going to get some people angry in this room. Do I need CDUs? Can I have the chiller talk directly to the racks? That has a set of problems on its own and benefits as well. And I think we have a really great opportunity at OCP to define this roadmap in a similar way where we said for liquid to air, we have rear door and we have sidecars, and probably sidecars is the right thing to do. I think we can, and I know some of those CDU work streams are starting. I think there's an opportunity to define the different use cases for all these options that I mentioned of CDUs. And we're probably going to need all of them, actually, for the different use cases, but we need to define those interfaces better.
Yeah. Paul, did you have something
to that? What we tend to see is transition to liquid, you have this huge improvement in your cased ambient, massive versus air. It's great, and we're moving much more power. But that's kind of like, we don't have any easy steps after that. So we're chasing degrees. So to your point, I think that thermal interfaces really make a difference. I mean, there's some implementations where you have a CDU to a heat exchangers to your facilities, you isolate that loop from the facility loop, and we're just adding interfaces. Same with the packaging, right? We have a TIM1, an IHS, a TIM2. So when you're chasing degrees, and it's degrees, it's not multiple degrees, you've got to look at all those interfaces, and how do we go from chip to environment the best way possible? And having a CDU, having a heat exchanger to isolate the loop, having multiple TIMs, those are things that are hard. And I don't think anything's easy going forward. When we're talking about 3,000 and 4,000 watt chips, we've got to go after kind of the harder things.
Yeah, and you touched on it a little bit about the requirements for CDUs and such. Can you talk, Paul and Chris and Husam, about TCS temperature requirements? Like, where do you guys see things going as far as that goes?
Sure. So we started the discussion probably about 4 years ago. Chris Moon actually, he's at OpenAI now, but what we wanted to do as an industry, when we looked at liquid cooling, I think the people we sold liquid cooling for so long, people thought it's infinite capacity. We're like, it's a lot better, but it's not infinite. And there was a lot of discussion around, I'm gonna do 50 degree, 55 degree water temp, so I'm gonna do heat reuse. And we're like, that's great on a CPU. You can do that on a memory, a hard drive, but I don't think it's gonna work on our GPU roadmaps. And the other side of it, we wanted to kind of say, hey, where's the bar? And I'll go back to when we did ASTRAE, right? We did A1, A2, A3. So we said, we're going to start at 32, 35, and we're going to add 40 and 45 for these higher temperatures. And we kind of lined the industry around that. Later, we added H1 because we're like, well, 32 is too high for some architecture. We're going to go to 25. So we wanted to align. So as an industry, we kind of said, we see 30 as the bottom. I'm not saying you can't go higher. I mean, it's great to use, if you can do dry cooler, if you can do economization. But we kind of saw 30C as the floor. We went, OCP worked with ASTRAE, and ASTRAE defined the S classes. So traditionally in liquid cooling, you just have facility. And so I have a facility temperature of 17, 30 degrees. And as an IT vendor, it doesn't mean anything to me, because I could have a facility water at 17 and a 30 degree TCS or a 20 degree TCS. And so we said, we got to have, as an IT supplier, I've got to know TCS. Facility water is great for a data center. For the rack, you need a TCS. So we kind of defined that. And then went to ASTRAE and we said, well, what do we need there? So we said, we're going to do 30, 35, 40, 45. And then about a year later, we're like, I think we might need to go lower, just in case. We don't want to make big changes. We're not, so we went to 25. There was discussion about 20. But we want to have a common bar. We're looking at 30. I think there's a lot of discussions of maybe doing dual loops. So your Cray, your rear door heat exchanger is going to have chilled water. A lot of these things are 30, like power supplies. The latest power supplies are 35C or lower. You can't use 40 degree water to a Cray and have that. But long term, I think we will likely, a lot of the scale up AI is going to settle towards 30. Now, if you're doing CPU, other workloads, I think you can go higher. And we'll see. I mean, we're chasing every degree. I mean, I think everybody wants to be higher. Everybody wants to, we're going to stay at 40, and we're going to try and not to go below 30. We're trying to set that as the lowest bar.
Yeah.
I'd like to add to Paul's point. We love higher temperature is good. If we can get all the performance we can get, no sacrifice in performance, the higher facility water temperature is better for the data center. And let me tell you the story from the data center side. So yeah, the higher temperature is good for your average PUE, so efficiency-wise, but it's also important for peak PUE, because that means you need to spend less energy on cooling and more energy to deploy more GPUs. So you got to take that into account as well. Now, some of the future things we're trying to enable, like for instance, we're working on microfluidics technology. Remove all these layers, bring the coolant inside the silicon itself, then we could actually go to much higher temperatures that we cannot do today because of the different thermal resistances. But that's something we'll need to continue to develop with the industry to get it to the next level. Also, looking at the data center, it has GPUs, it has CPUs, it has storage. Some portion of the load is air-cooled, some of it is liquid-cooled. You have personnel, all these things you have to take into account. So, like multiple loops is a possibility that some of your hardware will take higher temperature, some of it will go to air handlers, some of it go to CPU. And this takes us back to fungibility, because we want to be able to build those data centers to house all sort of SKUs. And the turn cycle or the technology refresh rate on hardware is so much faster. Like every couple of years, we're getting a new generation of hardware or GPU, and the data center is a longer lasting asset, 15 years or more or less. So how do you ensure that your data center building continues to be welcoming for all these varying SKUs across general purpose compute, cloud, and GPUs? So we need to also take into account the fungibility when we're doing these designs.
Yeah, the only thing I'd add, totally agree, is I don't think temperature is going to go up. I think you're just going to see that power dial go up. Because, 6 or 7 years ago, we were talking about 250-watt GPUs, and now we're 2,500, 10x in 6 years. And I keep looking at that hockey stick and saying, we're going to hit an asymptote somehow. But now we're doing, 500-watt kilowatt racks, right? And we're getting all these power supplies and bus bars. We're talking about 400, 800-volt DC. I'd love to see that, but it just, and the reason power is going up is it's scaling with performance. We're not just throwing power there for no reason. As you keep continuing, like on the compute side, you generally throw power at it, you hit this asymptote where you're really throwing a lot of power and you're getting a little bit more performance. You're like, it's not really worth it. It's running a little bit lower, get better performance per watt. But on the GPUs, you just crank it up. And everything's in the package. It's all scaling within the package. You really see the performance.
Yeah, just we've been covered pretty much, the one side of the fluid loop, the TCS, temperatures, and all that. What about the facility side? Maybe if you can cover that.
Yeah, so there's a couple things there. So, the heat rejection side is still, there are a lot of discussions around how the heat rejection side is really going to be what defines the real estate required essentially for a data center. As all the IT continues to condense, and your white space gets smaller and smaller, if you're rejecting that to air outside, you still need a lot of real estate to do that. So even the idea of like a CDU-less system where you'd run it directly to the heat rejection, then you're talking about potentially heat rejection that's large enough and distributed enough that you have a pretty big blast radius just to get that fluid where you need to take it. So there's a lot of discussion there, and we talked about this a bit. But I think it's very interesting right now, the progression of CDUs and seeing that, you get to a certain rack density where an in-rack CDU isn't really feasible anymore. It's taking up more of the rack than the compute is, so it doesn't make much sense. And so then you go to the row-based CDUs, and then potentially, those are serving a handful of racks, and you want to continue to expand that and drive to more of a skidded CDU to support more. Then as we approach this 1 megawatt rack, and Paul, you touched on this earlier, it becomes a big question of, a 1 megawatt rack is like a 4-inch pipe, right? So every 1 meg rack is going to need a 4-inch connection. So if you're trying to serve that from like a gallery CDU or a skidded CDU solution where you're trying to serve 5, 10 megawatts, I mean, you're easily approaching 8, 10 plus inch pipes driving out into the data center to distribute that. And then if each rack has some sort of flow control on it, because you're serving multiple racks from a CDU, now you're talking about flow control valves that are 4-inch. I mean, the cost, the weight, the complexity, the blast radius becomes so large. Your comment earlier about, does it become pulled back more to like almost like a 1-to-1 CDU per rack at that point, is an interesting discussion. Because there's a limit there somewhere where how big and, how big do you want your pipes? How much fluid do you want flowing? How much cost in your pipe work? How big of a blast radius do you want to accept before you kind of drive it back in and make it 1-to-1 when you get that 1 megawatt plus density?
Anyone have anything to add there?
I think the other thing is interesting is we start looking at some of the dynamic nature, right? So you look at GPUs, and you might see it at the grid. I mean, these are massive dynamics. And we're starting to see that on the CDU also, and having to have reservoirs to manage those transients. How do we respond fast enough? How are you power managing it? We're seeing a lot of that. We're going to put in my UPS for my chilling separate from my hardware. Yeah. So a lot of it gets really interesting how you do it. I think another thing that's kind of interesting is as we talk about getting enough power. So what a lot of people are doing is they're doing turbines. They're doing diesel generators. And as I said, I don't think it's useful heat off a GPU is that interesting, but useful heat off a generator or turbine, you can use that. That to me gets interesting. Robertson cycle and use that to chill your stuff. So I think it's just really interesting because the technology is evolving so fast that things that would make no sense 20 years ago, there's an economic reason to go. The technology's changed, so it's really interesting times. How you build a data center is so much different than it used to be.
And I would add to that, I think the point that Paul just mentioned, so the nature of AI workload, so that has an impact on power stabilization, and Microsoft had a presentation about it yesterday, but that also has a ramification on the cooling side. You need some thermal mass dampage, if you want to put it that way. And then that goes back to Chris's point, well, you need to build those somewhere, and those, they will take real estate. Going back to the, I want to maybe double click on the skidded CDU. I think one of the good next steps for us is to define what is the capacity or some of the design criteria for those skidded CDUs. Like, what is the sweet spot of capacity, cost, blast radius, and maybe there are some solutions, like you could have it modularized, not one heat exchanger, but multiple. Like, there are all sort of solutions to think about the blast radius as well, and I think there's no better place than OCP to define those.
Awesome, thank you all. So we're coming towards the end of our time. From a OCP perspective, Berhanu and I would love to have everybody involved in the community, so please, we're a community-driven subproject, so please join. Please bring your ideas. And we'd like to ask our panelists, what's your call to action for the community? Paul, do you want to start?
I could start. It came with the keynotes. Everybody already understands that power and cooling is a limitation. Just be active. There's plenty of work groups to get involved in. Come to the table with ideas. We're open about, hey, we've kicked off plenty of work streams. We just did a PG25, we're doing filtration, the CD work group kind of is added. So come here with ideas, come with workloads, let's work together. I think everybody sees this as we have to work together to enable the architecture and be more efficient. We're not going to be proprietary. I don't think anybody wants to be proprietary. We want to just, how do we scale this out and work together?
Yeah.
I think I have three things in mind. One is tactical. So the coolants, the different sources of coolants, I think we need to establish more interoperability, say PG25 or other coolants that are being used, just to enhance the supply chain and enhance deployment and serviceability. It's no longer that we have a small HPC cluster somewhere. Those things are being deployed at scale. We need to think about it differently. Another thing is systems thinking. When you're designing any of these cooling solutions, I encourage everybody to think as a chip supplier, but also think as a data center manufacturer or builder and operator, because that will switch some of the priorities. Again, go to cold temperature, I get more performance, but can I go just low enough in a way that I don't sacrifice data center efficiency and capacity, so I can deploy more GPUs? So, just that trade-off needs to be kept in mind. And the third one is I think we're facing a lot of unprecedented challenges with those densities and those architectures. So I encourage us to also think outside the box. Let's also go and seek those cooling solutions like microfluidics, power solutions, solid-state transformers, high-temperature superconductors, the network like CPO and other venues. I think it's time to also do some courageous innovation because the challenges are big.
Chris, you want to close us out?
Yeah, absolutely. So, it's essentially in the same vein of collaboration. My, perspective is slightly different just because of what my day-to-day is, which is fluid distribution, manifolds, basically row and rack. So for me, some of the stuff that's really valuable going on at OCP would be, we see the UQD and the UQD V2 work stream. We saw shortly ago in this room the PBMC work stream they were working on for another coupling. And some of those are moving into the marketplace on top of the proprietary couplings of which there are a number of different vendors and product lines. So, some of the stuff that's challenging on the manifold side, particularly in the rack, is things like make, model, size, gender, and quantity of QDs per server, which is different for everybody and everything. So continuing to work together to drive some more standardization on that, whether that's driving towards some of those PBMC UQD technologies, to make that a bit easier. And then fluid distribution at the row as well. We have a modular TCS work stream that's going on that talks about modularizing the TCS pipe work. We have the coolant fluids work stream to talk about filtration and fluid things. So there's plenty of places to get involved. Obviously, I think there's a lot of ground to make up. We all know there's plenty of problems to solve, and there's plenty of business to be had. So I think we need to keep working together on that. But those fluid distribution and best practices stuff is top of mind for me. So I'd love to see people in those discussions.
Thank you. Let's thank our panelists. We're at time.